Greetings, ladies and gentlemen. My name is Michele Pompilio, and in this video I will tell you about my PhD project. I will also tell you about a few key concepts of the physics behind what we study at BIP, which stands for Bio-Inspired and Bionic Materials for Enhanced Photosynthesis. Welcome to the lab! First, allow me to tell you a little bit about myself. I was born and raised in Italy, and I graduated in physics at University of Pisa. Now I'm early stage researcher number 5 within the BIP project at University College London and at the London Centre for Nanotechnology. My job here is to get a better understanding of how some marine organisms, mainly diatoms and corals, manage light, and hopefully to exploit this knowledge for the design of biomimetic or bionic organic optoelectronic devices. Before moving on, however, let's go to another lab. You'll see why in a bit. You see, organisms like diatoms and corals have, over the millennia, evolved fascinating photonic structures which allow them to interact with the light coming from the sun in some very intriguing ways. There are many other examples of photonic structures in nature. These are what gives some butterflies or plants their bright colors without using any pigment, or what makes some beetles or gemstones, such as opals, iridescent. Interestingly, we can replicate these structures in our labs, as shown by this beautiful synthetic opal made by Dr. Tecla Arcidiacono, a former PhD student in my group here at UCL. Allow me to explain it better. One of the key aspects of these structures is that they have structural features that are small enough to be comparable to the wavelength of incoming light, as is in the case for the nanospheres that form our opal. This can lead to multiple reflections and scatterings, after which the light wave can interfere with itself or with other waves. This means that light waves with different wavelengths, i.e. different energies, interact differently with the photonic structures. Some of them may be completely reflected back, for example, as is the case in a photonic crystal with a so-called photonic band gap. What wavelengths are reflected can also depend on the angle of incidence of the light, resulting in a phenomenon called iridescence. And now, the reason why we moved to this lab. Let me show you these concepts in action. What you can see here is a very simple setup in which I can shine white light coming from this lamp onto the opal I just showed you, and this can be done from different angles. What I'm going to show you is the reflected light from the opal onto that white screen. Let's turn off the lights and begin the experiment. Now, if I change the direction of incidence of the light, different wavelengths will be reflected, resulting in the reflection changing color. This is iridescence, and it's the same principle behind, for example, Alvaro's bacteria. This concludes my video. I hope you enjoyed it, or perhaps you learned something new. Thank you very much for watching, and have a good day.